All right, team, let's take a look at homework number 6. We're going to be walking through part 2 right here, where we're doing flood frequency analysis and comparing different methods. I give you a PDF that gives you a walkthrough from Oregon State University on how to do this for Log Pearson type 3 and to do it in an Excel spreadsheet. I'll be walking through that and talking about the other methods that we're using as well. So you can download this PDF as a walkthrough, and then I've posted a template spreadsheet to use as well. We're going to be using Canna Creek data. So the first thing we'll do is Google USGS Canna Creek. That brings us to the NWIS website, the USGS website for that stream gauge. We look at a summary of all available data and we click on peak stream flow. That runs from 1918 to 1983, shows all the peaks here. If I were doing this for a design on an actual project, I'd want more contemporary data, more recent data. So it stops at 83. I'd want something that has at least kind of past 30 years, 20 years, something like that of data that represents kind of the modern era. I'm going to click on tab separated file. And then I'm going to do Control A and Control C to copy all that data. And then we're going to bring that into Excel by creating a text document. I'll just call that Canna. Open it up, paste it in there, save it. And if you have an Apple, you can do this with some sort of notepad type of program. Then I go to Excel and I create a new notebook. Open, look for that text document, and I have to select all files here so I can find that text document. Now it's gonna, we wanna click delimited here for this import wizard. That means how do we divide the columns? Tab delimited is the default. If you scroll down here, you can see that it's drawing lines where we have tabs. So that creates columns. I press finish, brings my data in. Great. Peak value is what we're interested in. We can keep the date as well, though it's not necessary. I'm going to delete this header information and we'll just keep this right here. And delete all this stuff, we don't need it. That's all extra. So USGS data is always going to be CFS. So I'm just going to add those units there so we can keep track of that. The first thing we're going to do is the Weibull method to plot this. And to do that, of course, first we do the rank, and then we do the probability of exceedance, P of E, which is equal to M over N plus 1. M is the rank, and N is the number of observations we have. We've got 64 observations, right, minus that header. So I'm going to just put that there. And then the rank is going to be 1 for the highest value. So we can sort these data. I selected those 2 columns. I go to data, sort. It says my data has headers, so it just selects those values. We're going to sort by peak value, largest to smallest. And there it is. Here's our rank. So we put 1, 2. Excel can pick up patterns sometimes. So if I select those 2 and click on that dot, double click, it'll paste up the rank all the way down for me. Now I'll enter the formula for probability of exceedance, 1 over N plus 1. And we want to make sure that N doesn't move. So I click over that in the formula, press F4 or function F4, puts it in for me. Double click on that box and it'll copy the formula all the way down. Put recurrence interval in years. which is just the reciprocal. So with my data set of 64 observations, I can predict up to the 65-year recurrence interval flood event down to the 1 year. So you're going to make a plot of that, and I'm going to zoom over to the spreadsheet I've already created, where we've created a plot. If I want to get exact values for, say, the 2-year, 10-year, 50-year flood, I can use linear interpolation between those events. So here is my 50-year flood. It's going to fall between 65 and 32. So I just used linear interpolation to calculate that value right there. We're going to compare these values later, so that's why I did that. And then here's my graph. I have annual exceedance probability in percent on the x-axis, and then peak discharge on the y-axis. Got a log scale on both, and I've reversed the axes values. So I've got kind of the 99 or the more frequent floods over here, and the less frequent floods over here. The next thing we're going to do is fit the Log Pearson type 3 distribution to the flood, so we can extrapolate out and predict more than the floods that are less frequent than that 65-year event. So the reading for this is in Betty and et al. Section 3.3, and then we also have an example in the textbook that you can take a look at. I've got the same data here. That PDF file that kind of gives you step-by-step from Oregon State has you first have your peak discharge values. So that's our CFS. The first step is take the logs of that. So the Log Pearson type 3, which is the distribution that is used by USGS and Army Corps of Engineers, kind of the standard distribution we use to predict and extrapolate out for less frequent flood events. It's based on the logs of the discharge. So the first thing we'll do is take the logs of everything. This is log base 10. And so that's the formula. And so we take the logs of everything. Then to calculate the variance, standard deviation, and skewness, what we'll do is first, we'll subtract each log discharge value. We'll take the average of that down here at the bottom. And then we'll subtract that average out from each individual observation. So log Q minus average of log Q. And paste that all the way down. Now we'll take the square of that, and this helps us get the variance and standard deviation. So just the square of the differences. And then we'll take the cube of the differences. At the bottom, I've summed these up. And then if we look at the formula for right here for calculating the variance, the standard deviation, and the skewness, all of these involve either the square of the differences or the cube of the differences. So I've calculated here the variance of my log discharge values based on the sum of the squared differences divided by n minus 1. Standard deviation is the square root of the variance. And then the skewness, that's a little more complicated formula right here, but it involves the sum of the cubes of the differences and then ends, and then the standard deviation cubed. So that's this formula right here. So now that I've calculated that, I can kind of move on to the other steps. Also note that you can use internal formulas. So I've got standard deviation. Of course, you can just use standard deviation and select all the values of the logs. So standard deviation of the logs. And then Excel also has a built-in skewness function, just called skew of the logs, and it will give us about the same value as we calculated over here. We'll note that by calculating the skewness of the logs of our data from the USGS gauge, that's the station skewness. And I talked about in class that for this method, we use what's known as a weighted skewness. So we could take our station skewness, our gauge, and we'll note that if that's a small sample size, it's going to be not a great kind of estimate for our data and for fitting that distribution. So there's this method. It gets a little bit into the weeds. I'm going to have you guys skip over it. where we take a regional skewness, which is based on this map. So regional skewness values for floods in across the country. And you'll note that this contour is -0.3 that goes right through Grand Junction. So we use that -0.3 for regional skewness. We do this weighting scheme, and we end up with a weighted skewness that kind of gives some weight to regional skewness and some weight to the station skewness. That ends up being really close to our station skewness. So, and at the end, not a huge difference. This value you'll use in the next steps. So now that we've calculated the weighted skewness value, we can go to a table that's provided in the PDF value. I've also included it in this Excel spreadsheet. And what it does is it says given for a given weighted skewness value, and they range from 3 all the way down to -3, and a event, it gives us a K value that we'll use to plot the Log Pearson 3 distribution through our data points. I'm going to go back to this tab real quick. This is the equation that we're using to fit our Log Pearson 3 probability density function to the data. So what it says is for a given Q peak value and the log of that is equal to the mean of your logs of your peak discharges plus this K value, which is a function of the recurrence interval or the frequency and that skewness, times the standard deviation of our the logs of our peak discharge values. So this equation has the form of a line, and it's ultimately a function of the means, standard deviation of our logs of our peak discharge value, and that K factor. So the first step we'll do is actually estimate the K factor. And what I've done here is for a given annual exceedance probability in percent, we can go to that table, and we'll note that our estimated K factor is -0.295, which falls between these two values. So I've taken these two values and all the associated K factors, I've pasted them over here. There's for -0.2 and here's for -0.3. And then I put in our estimated weighted skewness value of -0.295. Then using linear interpolation, I calculate the K factor for our weighted skewness for all these annual exceedance probabilities. And that's what these values are right here. Now we can go to the final step, which is to actually plot our points. So here's the annual exceedance probability, percent and probability. Here's that K value that we just calculated with linear interpolation. Here is the logs of my Q peak values that I'm calculating using this equation right here. So all I'm doing is taking the average value from up here, and then I'm adding the K value times the standard deviation, and the standard deviation we calculated up here. So these two values don't change, it's only the K value that changes. So if I drag that formula down, I get an estimate of the logs of the peak discharge, and then all I need to do is transform that by exponentiating them from 10. So 10 to the log 10 of some value gives us units of Q peak in CFS. So now that I've done that, I can actually plot the fitted Log Pearson 3 distribution over my data. And so that's what I've done here. We've got the annual exceedance probability on the x-axis, that's before peak discharge on the y. And then this green line are those points that come from these data. So annual exceedance probability in percent, and then the peak discharge. And all I'm doing is plotting that as a line through my data. And you can see that it does a decent job of fitting. It overpredicts for lower exceedance probabilities, and at some point it kind of underpredicts. So it's got its limitations, right? But this is how we use then. We can say, okay, what is our 1% annual chance flood and up to the 200-year is what we did here. And if we go back to our Weibull frequency analysis, you'll note that we only can predict up to the 65-year recurrence interval event. So good job, you fit the Log Pearson 3 distribution to your data, and you can use that then to extrapolate out and predict flood events beyond your data set, such as these. The next step is we'll actually use Erams to do the same thing. So I'm going to click on this link, and it's going to bring me to the Erams website. This is an online tool that we can use to do the same thing for gauge data. So we'll log in. You can create a profile for yourself to log in. It's a free account. I'm going to create a project. We'll call it CANA 2021. The project type will be a flow analysis. And then we'll say, okay. So there's my project. I can click on that to open up a map. And this map, I want you to take a minute to read through this, but we'll be looking for USGS NWIS gauges. So we can actually search for that. I'll do CANA Creek, and we'll search for that gauge. There's our gauge, and it comes up down here. So you don't need to zoom to it. We'll just click on the blue dot or the blue pin, which is the USGS gauge. I click on that and it brings up the gauge. It tells you the date range, the flood data, the range of that. And then we'll click on this flow analysis model. We can go to flood tab, and we'll just check the data. And then what we'll do is click on run the model. We don't need to change anything here. So it ran the model, which is basically doing the same thing that we did in Excel, except now it's done this for you and given you a plot. So here is our estimates of peak discharge. There's a little bit of a formatting error, but this is your estimate of peak discharge right here in the middle. Gives you a lower confidence interval and an upper confidence interval. And here's the return period. So you can actually copy this table, Control C, and then you can paste this into the Excel spreadsheet right here. So that's what I've done. And then now we can plot our estimates of peak discharge and an upper and a lower confidence interval in Excel. And I've also pasted the plot here that Erams gives you. This is a straight line because they have a different x-axis. The x-axis is kind of spread out in a different way that allows it to plot as a straight line. The last thing we'll do is stream stats. So you'll go to stream stats and you'll find CANA Creek. You'll delineate the watershed, where that stream gauge is, and stream stats will show you the stream gauge location. So just zoom in where the stream gauge is. You don't want to click on it. Just make sure you delineate just downstream of the stream gauge. So that's what I've shown here. The stream gauge is a little blue triangle right there. So I clicked just below it and delineated a watershed above that stream gauge. So we'll run the stream stats report and you'll get a bunch of information. I took the table from the Northwest region, and then it has a peak discharge for the 100-year flood of 1350 CFS. So I've plotted the table here, and I've also included the standard error of projection, or SEP. And this is a percent. The way we can interpret this as is a kind of plus or minus percentage of the estimate for our error. And so the way to calculate it, kind of an upper and lower one, is to simply take that percent divided by 100, right? And then multiply it by our Q-peak estimate. So that's going to be a low estimate, and then the high would be to do the same thing. Let's see here. And then we can actually estimate the error by subtracting or finding the difference basically between the upper and lower of these. So what I've done here is I've plotted the Weibull frequency here, the first step, and then we've got the stream stats estimates in black, and then I've got error bars showing that kind of plus or minus error associated with the stream stats estimate. So you can see there's a kind of quite a big error, but the stream stat estimate actually lines up pretty well over Canna Creek. All right, so now the last step is to put it all together. So I asked you to, for the 2-year up to the 200-year flood, to put a table together. And so we're going to do the Weibull method. We're going to have the Log Pearson 3 that you did in Excel, the one from Erams, which is going to be a little bit different, and then stream stats. And then what I ask you to do is create a plot to kind of plot everything on top of itself. So the Log Pearson 3 from Excel and Erams should fall pretty much on top of each other. You can include the confidence intervals here. I've done that with a red dashed line. Stream stats estimate with the error bars, and then my original kind of just empirical estimates. And that is the final step for this project, for part 2 of the homework.